Akansha Garg. I will introduce our background. Dr. Akansha Garg received the BTech degree in Electrical and Electronics Engineering from the Rajasthan Technical University, India in 2013, and the MTech degree with specialization in Power Electronics and Systems from Manipal University, India in 2015. She received the PhD degree in Electrical Engineering with the School of Computing and Electrical Engineering, Indian Institute of Technology, Mandi, India. Post her PhD, she worked as a knowledge associate at Center for Development of Advanced Computing, CDAC, Bangalore, India, in 2022. She is currently working on a UKRA funded research project at University of Manchester as a postdoctoral research associate. Presently, she is investigating the expected challenges and prospective work around to integrate next generation storage unit into the power system. Her PhD research work includes the designing of the microgrid model to ensure real-time power management in DC microgrids using a reliable distributed control technique. Her current research interests include integration of storage units into power system, telecommunications application in power systems, power management in microgrids, renewable energy resources integration in smart grids, distributed power generation systems, and power electronics converter. With this introduction, I like to welcome our speaker, Dr. Akansha Gar. Yeah, you please start now.
Yes, sir. Thank you for the introduction, sir. And thank you for inviting me for the talk in the faculty development program. I hope my topic of discussion would be of interest to the joinees and to the faculties who have joined the program today. I'll start my presentation. I'll share my screen. Please let me know if the screen is visible once it
Yeah,
is shared.
yeah.
Yeah. So is my screen visible?
Yeah, fine.
Yeah. Thank you. Thank you for confirming, sir. So the topic of my presentation is real-time power management in DC microgrids. This is the research work which I did during my PhD, and presently I am working in the similar area but with different problem sets and different objectives. So today I'll be discussing some of the research objectives for which we have already carried the prospective work and have published the same. So once again, I'll thank you, Tirumugan sir and Shivam sir, for inviting me for the faculty development program. So the outline of my presentation today will include the introduction, basic introduction to microgrids, the need of power management in the microgrids, then the overview of the real-time power management strategies in the microgrids, which has already been there in the literature, which is published by different researchers, and then the focus on the distributed DC bus signaling type of power management technique, which is the technique which I considered for my work, considering the overall aim of my project work to be in the area of rural electrification, to be specific, and then going into detail that developing of the modularized model and also analyzing the simulation as well as the experimental results which I obtained from the research work, followed by the different sub-objectives, which was the effect of cable voltage drops in the real-time microgrid system and the implementation of different energy management scenarios, etc., followed by the conclusion. So starting my presentation with the introduction to the microgrids. So the microgrid in journal is a term which is called for an electrical network which comprises of a distributed energy resources. For example, we say solar PV as well as wind, etc., as well as the storage systems and loads which are available in distributed network. Basically, the microgrids are of various types, which are called the AC microgrids, DC microgrids, as well as the hybrid microgrids. In AC microgrids, the main bus is a AC bus where all the sources as well as the loads and the storage systems are connected. However, in the DC microgrids, the main bus is the DC bus, and in the hybrid microgrids, AC as well as DC buses are present. The relevance of microgrids in India is because of the following points which I have mentioned. That is because, first of all, the large power consumption. As we all know, the requirement of the power in the country is comparatively more than what is already available or what is already generated in ground. So that is the main focus of the work, that microgrids can help generation of the electricity in an alternative domain which can be used, and hence the larger section of the power can be supplied through the microgrids as well. Also, the reliability of the power increases because dependency not only on the AC grid system, whereas the distributed networks also increases. And also it helps in reduction of the pollution at the higher end, because the microgrids are generally being discussed with the whereabouts, including the solar PV, etc., as the sources. So these are few points why the microgrids are important in India. So the work which I proceeded with for carrying out the research was in the area of DC microgrids because of the following pros which it holds. That is, first of all, considering the solar PV, which is one of the main source of generation of the DC power, is is also a DC source. Hence, it can be directly connected to the DC bus in the DC microgrid, which is shown in the DC microgrid system here. So the DC solar PV can be directly connected to the DC bus through a DC to DC converter. Also, the state of art of the efficient loads are DC loads. So there are various companies which are coming up in India. For example, Signi, just for an instant. So they provide the DC loads in the market, and nowadays DC loads are becoming the state of art efficient loads, and hence the loads can be directly connected to the DC bus, as we were discussing about the solar PV. Also, the DC microgrids are considered to be cost effective and more efficient as per the literature, because they include less number of converter stages. That is, DC, if it would have been a AC bus, then the solar PV would have been giving DC power, which could have been connected to a DC-DC converter for changing the voltage levels, and also then it would be connected to a DC to AC converter to connect with the AC bus. Similarly, it would have been with the load side, that is AC to DC converter and then the DC to DC converter. That means an extra conversion state will be added for all the entities connected in the microgrid. Hence, to save on with one conversion stage and to make it more efficient, because addition of the converter stages adds to the complexity of the system as well, and also decreases the efficiency of the complete overall system. So in that way, the DC microgrids are considered to be more effective, cost effective, as well as the more efficient network. So this is one DC microgrid system, a generalized DC microgrid system, which is shown, which shows different entities to be connected to the microgrid through the relevant converters, and also the loads can be seen here. And the AC microgrid can also be AC grid system, which is already in place, can also be connected to the DC microgrid through a DC to AC converter, wherein the AC microgrid can be acting as a backup power. So the next topic of discussion is why power management is required in DC microgrid. As we all know, the uh, renewable energy sources, for example, solar PV or the wind power, which is available from the wind plants, etc., are very intermittent in nature. That is, it depends in the real time whether it is sunny or whether it is windy. Based on that, uh, the real power available might vary. Hence, due to the intermittent nature of the renewable energy sources, and also due to the varying load demand, and with the reliability expectation of the customers and the consumers, the power management in the microgrid needs to be studied. That is, it needs to be made sure that in real time the power is always managed in the microgrid. Also, if the power is not managed, the DC bus voltage will not be regulated, which will eventually affect the loads as well as the sources in the sources connected in the microgrid. The next point is also that it helps the managing of the power in the microgrid also helps in effective utilization of the entities. The effective utilization of different entities and regulation of the power will be discussed in greater detail in the further slides. The power management in the microgrids is basically divided into two types of power management control strategies, which are centralized control as well as decentralized control. The decentralized control is then further divided into two types of strategies, which is decentralized control with dedicated communication link and without dedicated communication link. So just to bring the highlight of different control strategies, first of all, putting the focus on the centralized control technique, power management technique. In this particular type of control management technique, there is always a central controller which is sitting in the network, which determines that what each entity in the microgrid needs to do. For example, solar, wind, battery, or the loads, or the AC grid, in what state are the different entities present will be determined by the central controller sitting in the microgrid system. So here, the high-speed communication network is also present, through which the central controller will communicate with different entities present in the network. So the entities communicate with the central controller via communication link through the communication unit, which is shown here as CU. Also, the local energy management unit is present for each entity in the network. So, for example, if there is a particular amount of power available with the solar PV, so this power is being read by central controller at all time in the real situation. So, based on the availability of the power with the solar or with the AC grid or with the requirement of the load power, the central controller will take the decision that how much power is being sent through which entity to load. So the overall consideration is being done by central controller as well as the high speed communication channel here. However, with these considerations, there are few advantages of this technique, which are that this technique provides a good speed of response, as well as the DC bus voltage will be very regulated, because the central controller will be taking the actions in the real time and will be letting each entity know that how everything needs to be planned in the system, and the DC bus needs to be regulated at a particular voltage. So this is optimally being done by the central controller here. However, there are limitations to this scheme, which is that the system is prone to the complete system failure, as if the central controller fails or if the high speed communication link fails, then there is the local controller here will not be able to manage the system in such a way as the central controller was doing. So in that case, the complete system or a part of a system failure needs to be taken into consideration, and hence we can say that the system is not that reliable. And also the system is costly because of the additional cost which is incurred by the addition of the central controller as well as the communication channels here. So for detailed study of this, we have some references here which can be taken into consideration further. Also, the other type of technique is the decentralized control, in which only the central controller is not present. However, there is an additional communication channel which through which all the entities are communicating with each other. So the features of this scheme also is that the explicit communication channel is present for communication among the different entities, and the however the system does not shut down completely if any controller fails, because here there was no central controller who was in the first place taking all the decisions. Here the decisions are taken by the individual entities itself. However, they are communicating through an external communication link. But similar to the previous strategy which we were discussing, this scheme also has a limitation because of the reliability issues of the external communication link which we are talking about, and also this definitely adds to the cost of the complete system. The third type of technique, which is called a distributed control, or also called a decentralized type of control, but without the external communication link, as we can see here, that there is no external communication link, and the implicit communication is present directly through the DC bus voltage, which is shown here, and the control action in the system is distributed based on a predefined set of predefined set of values, or a um, predefined set of nodes, in which every entity will be given a particular range of bus voltage, and based on the detection of that bus voltage, each entity needs to define the mode of its working. So in the detail, in the further slides, we will be majorly focusing on a distributed type of technique because of the following advantages. That is, this particular technique is considered to be reliable and cost effective because, first of all, there is no central controller whose failure might affect to the complete breakdown of the system. And secondly, there is no external communication link, which is also leading to the reliability issues as discussed in the previous type of strategy. So here, the focus for our further study will be in the distributed type of technique because of these advantages of the system which we are discussing here. In a distributed type of technique, DC bus signaling is a type of technique in which the control function is distributed among all the entities present in the network. So, solar, wind, battery, DC loads, or the AC loads, as well as the AC grid. The control function will be distributed in all the entities present in the network, and also the communication will be taking place only through this DC bus voltage. The DC bus voltage will be read by all the voltage sensors shown here, and based on the reading of these voltages of the bus, all the local energy management units will take the decision that how the entity needs, in what mode the entity needs to work, or what will be the limitation of the power or the current. That all depends locally on, with each entity, and not with a central unit here. So the entities are controlled locally by the DC bus voltage, as we have discussed already, and the entities are prioritized to regulate the DC bus voltage at a predefined level. So in this technique, all the entities have a preset value of voltage at which they need to regulate the bus voltage. However, if the voltage is not at the predefined level, during that time, the mode of the different entities are defined based on the local energy management unit in the real time. So the mode of operation of the entities will depend on the detection of the bus voltage. So as we have already discussed in the previous slides, that the system in this type of technique is considered to be reliable and cost effective. Along with the advantages, it has few limitations, that is with compared to the previous strategies, that is the centralized and the decentralized techniques with the additional communication link. This particular technique has a poorer voltage regulation, and also the extendability of the scheme is limited compared to the previous schemes. However, with the aim of electrifying the rural communities or the villages, the particular technique can be used for the microgrid system and has been tested for the simulation as well as the experimental results, and can be elaborated to a higher level for its implementation for the rural electrification. So in respect to the technique which we were discussing, that is the DC bus signaling technique, the research has already been done in the same area. However, there were few limitations or the research gaps which existed and which were addressed in the work which I carried out. And the major research gap was that we could not identify any modularized design for the microgrid to carry out the study of power management in the literature, and hence the work was done in the same area. And also in the previous research works, the concept for the rural electrification or for electrifying the remote communities with the integration to the AC grid, and for the loads which are rated for 48 volts, which are available in the market in the present scenario, the residential as well as the for the residential loads, the voltages are generally considered, for the DC voltages are considered in the range of 24 as well as the 48 volts. So the present work has been done for considering the voltage levels of 48 volts. So this study was not seen, and hence we carried our research in the same domain so as to study that how it can be effective for the residential domains. And also the control strategy was designed in such a way that uh, it had the limitation of number of entities which can be added to the network, because different voltage thresholds for supplying and receiving of the power via individual entity. That is, for example, if there is a battery, then for battery supplying and for battery power receiving, different range of voltages were considered. However, in the present technique, in the research which we carried out, we removed this limitation, and with the same voltage threshold level, the battery power supplying and receiving could be achieved. So these are the few scientific research gaps which we worked on and could successfully see the results in the same domain. So these are the few research objectives, the overall research objectives, which I will be discussing on in the further slides. The overall objective is all the time to achieve the real-time power management in the microgrid using the DC bus signaling technique, which is a distributed type of technique. However, the sub-research objectives are to design a modularized model of a DC microgrid by developing a general framework for power management, and to study the higher level simulation using a MATLAB design model, and also verifying the model, that is the experimental verification of the power management scheme and the designed model. And the other objective is to analyze the analysis for the selection of the voltage levels in the microgrid, and to study the effect of cable voltage drops in the network. And the other objective which was studied was, we proposed and implemented some energy management scenarios in the network. The quantitative as well as the qualitative comparisons were done, and which leads to the pathway that based on the user definition, different type of energy management scenarios can be implemented in the network. So starting with first research objective, which I was discussing in the previous slide, the modularized model of a DC microgrid was designed, which allows easy extension for various purposes such as long durational performance and economic analysis. So a 3-tier modularized model of a microgrid was developed. So this is the modularized model of a DC microgrid which was developed, in which it was divided into 3 models. That is layer 1, which shows the basic DC microgrid model, and which is also used for studying the power management in the microgrid. And the layer 2 was the energy resources model, which provided the maximum power in the power limitations in the real time. That is the maximum battery charging or discharging power, or for the AC grid, the maximum supplying or the receiving power to be specific, and the layer 3 model, which was the model for long durational analysis. So the study was performed, the study and research was performed considering the implementation of layer 1, followed by layer 1 and layer 2 together, and layer 1, layer 2, layer 3 together. So the focus of the present work is in the understanding of the layer 1, in which the basic DC microgrid model is designed, and the study of power management is being carried out. So here, the consideration of the microgrid was a DC bus is the main bus of the microgrid which we have taken into consideration, and the different entities, that is solar PV, AC grid, battery, as well as the local loads, which are divided into critical and the non-critical loads, were considered, and all the entities were connected to the DC bus by the respective power converters, and this was being managed by the local energy management unit of each individual, that is each energy management unit. So here the voltage is being sensed from the DC bus, and all the local energy management units are taking the decisions of the real time working of the different entities present in the microgrid. So this is the further detailed model of the microgrid, and here we can see that this is the DC bus, and just to show that one of the cases, that here this is the DC-DC converter for the solar PV. This is the solar PV which we are considering, which works as a voltage source or as a current source depending on the real time situation in the microgrid. Then this is the voltage sensor for the solar PV, and this is the local energy management unit, which based on the predefined set of rules is determining that what should be the mode for the PV to work in, and hence all the other decisions are being taken by the local energy management unit. Similarly, the local energy management for battery and the battery converter, the AC grid converter, and this is how the loads are connected here. So for carrying out the real-time power management in the microgrid using the distributed control, the general framework for power management was designed, in which this was the framework which was decided, that is the source priority, that is for supplying the power, the priority was always given to the renewable energy sources, so that the power generated from PV, which is a renewable power, should never go waste. The complete power should be utilized from the renewables first, followed by the power available from the AC grid in real time, which, and then battery provides the power, which is a backup power here, and then the if the overall power is not being supplied, required power is not being supplied by the renewable sources, AC grid or battery in addition, in that case the loads needs to shut down, the load shedding needs to be done. So this is the source priority, this is the load priority for a defined energy management scenario. So in the general framework decided, there were different levels which were designed. In level 1, if we can see, the PV will provide the maximum available power, that is the load power, if the AC grid is receiving or the battery is charging. So these complete powers are being fed by the PV. So during this time, the PV power should be in the limitation of the maximum power available with PV and 0, because PV power is a positive power, so 0 to PPV max. But if in case the PPV is not able to supply the overall power required by the different entities, that is AC grid, battery, or the load, in that case, the power supplying priority switches to AC grid. So here now AC grid is supplying the power, wherein the load is being fed, the PV is providing its maximum power, but the battery is also getting charged. In the similar way, if the AC grid is also not able to supply the power required by the other entities present in the network, then the priority will shift to the next, that is the battery. So here battery will try to provide the available power, required power by the different entities, follow after PV as well as the AC grid. And if in case battery is also not able to supply the complete power, then the load shedding needs to be done. And the other way around it goes, that how the power is being received, like uh, it is just the vice versa of the way which we have discussed already for the RES, AC grid and the battery. So the overall crux of the work is that the power should be managed in real time. That is the PPV, P battery, PAC and the load power should sum to be zero. So to considering the general framework which I showed in the previous slide, the simulation model of the DC microgrid was designed, that is in layer 1, the local energy management unit, the PV subsystem, and similarly for the other units for battery and AC grid, it was designed. And layer 2 was designed to define the maximum power limits which are being used here. That is based on the maximum power limits, the PV the determination whether the PV is working at maximum power point or it is working as a voltage source is defined. So these powers are being fed by the layer 2 here. So this is how the designing of the local energy management unit is done. That is based on the determination of the maximum power and the bus voltage and the defined level 1 voltage, which is for us, the nominal bus voltage is considered to be 48 volts, which I was discussing, as the residential loads are designed for 48 as well as the 24 volt system. So 48 volts being considered as the nominal bus voltage. The overall range of the bus voltage is considered here to be in the range of 44, 43, 44 to 50 volts. So here for the level 1, that is for PV, the bus voltage is considered to be 50 volts. So based on the designing of the local energy management unit, a JK flip-flop is used to determine whether the entity will be working in a voltage mode or it will be working in a current mode. So if in case PV power is in axis and the overall required power from the AC grid or the battery or the load in total is lesser than the power availability from the PV. In that case, the PV needs to be worked in a voltage mode so that the excess power is not, so that the power is limited to the maximum power required by the different loads. Whereas if the overall power is not being fed completely by the PV, in that case, PV needs to supply its maximum power and it works in a current mode. So this the selection of these uh, modes, that is a PV should work in a voltage mode or in a current mode, depends on the local energy management unit which is designed here, and the modeling is done based on this logic which is shown here. So the main aims of the simulation and the experimental tests, which will be shown in the further studies, are to verify the visibility of using the simple models of microgrid instead of the detailed power converter model. So here, as we can see, that a PV model is being used either as a voltage source or as a current source. So this is being validated by a simulation as well as a hardware test to see whether the feasibility of the simple models is fine or not, and also to verify the ability of the DC bus signaling scheme to ensure that the power management in the DC microgrid under various power flow conditions is being done, and to study the effect of cable voltage drops on the extendability of the DC microgrid. That is how the cable voltage drops in the network leads to the extendability of the DC microgrid, how it affects the extendability of the DC microgrid systems, and to showcase the implementation of different energy management scenarios. So this is one energy management scenario which we are showing. Similar to this, there are different energy management scenarios which can be varied depending on the user criterion. So that will also be the point of discussion in the further slides. For the simulation study and for the experimental validation of the first case, that is for showing the power management in the DC microgrid. These were the maximum power limits for the different entities. That is for 1000 watts per meter square. The maximum power availability from the PV was considered to be 118 watts, near about 118 watts, and the maximum supplying and receiving capacity for the AC was considered to be 20 and 24 watts respectively. And similarly for the battery, it was considered to be 36 and 36 watts for discharging as well as charging. And the load was considered to be around 35 watts, which was at 50 volts when the PV was regulating the bus voltage. However, this might vary depending on the voltage regulation by different entities. So the overall microgrid specifications, which were considered for the hardware experimental model, was designed for around 175 to 200 watts of the system and was tested for 20 kilohertz. And the nominal bus voltage was considered to be 48 volts. And the space was being used as a controller board for carrying out the experimental study. Also, the PV simulator, which was available for 150 volts, 5.6 amperes rated, was being used as a solar panel to emulate the PV characteristics. And the batteries were being used, which were like 12 volt two batteries were used as a 24-volt source. I will show in the future. In this slide, we can see that this is the laboratory prototype of a DC microgrid, in which this particularly shows the designed DC microgrid model, in which this part includes the inductors of different converters which are designed, DC-DC converters and the DC-AC converters. And these are the converters are designed using the IGBT switches. So, and these are the drivers, the level shifter and the D-space kit which was being used. And these are the voltage and the current sensors. The voltage sensor wherein the voltage is being sensed from the DC bus. So this is the voltage sensor. And here this is showing the regulated bus voltage at 50 volts when the PV is regulating the bus voltage. So the overall picturization of the laboratory prototype is here, wherein this is a solar simulator or emulator, which is from Elgar, and here we are showing the DSOs for taking the results, and here we are having the PV the PV app from the Elgar MTech, in which we can design the required PV characteristics in the depending on the irradiation and the temperature conditions. And here, and this is the zoomed version for this microgrid setup shown here. And these are the batteries and the grid side converter which is being considered. So the coming to the study, that is the simulation as the and the experimental study for verification of the higher level simulation. So a simplified DC microgrid model assumes that a power converter of a particular microgrid entity operates either as a voltage source, as was discussed here, that it will be implementing either as a voltage source or as a current source. So when regulating the bus voltage, it works as a voltage source, and when as a current source at other times whenever it is providing its maximum power. So the detailed modeling of the power converter was avoided in the simulation platform. However, in the hardware, the converters were designed. But in the simulation platform, the modeling of the power converters was avoided, and the power converters were assumed to be very fast, and the system dynamics were largely determined by the bus side capacitances. So here we can see that if we consider this as a inductor current, if we change the inductor current in the real time, during that time the sudden change in the inductor current was being tracked in a very short notice. However, with this change in the inductor current, the voltage took some time to settle to a particular value. As this is for the simulation as well as this is for the hardware, for the similar result. So from this one, we can see that the sudden change with the change in the reference inductor current could be seen in the inductor current. However, with the voltage, there was a relevant duration of time which was required to obtain a static voltage. So from this, we could see that the system dynamic is being largely determined by the bus side capacitances, and hence we considered that the system can be either considered to be working in a current mode or in a voltage mode. So based on this assumption, the complete modeling of the microgrid was carried out. The next section shows the results in real time of the real time power management in microgrids using the distributed technique which we were discussing from the start of the presentation, implementing on this particular energy management scenario in which the priority is given to AC grid, followed by the battery, non-critical loads and critical loads, wherein the renewable source is always given the first priority. So here we can see that from 0 to T1, the overall power available with the PV is 118 watts. As I told that it is the maximum rated power for 1000 watts per meter square irradiation. So during this time, the availability of the power from PV is 118 watts. However, the load requirement is only 35 watts. Load requirement is only 35 watts, and as well as the battery is requiring 36 watts of power, and the AC grid is requiring 24 watts of power. So overall, the power required from the entities present in the microgrid is only 95 watts. However, the maximum power available with PV is 118 watts. So the PV at present is not working at maximum power point and is working as a voltage source regulating the bus voltage at 50 volts, which is a predefined voltage for the based on the predefined set of rules. However, with the change in the irradiation condition, we can see that as the irradiation changes from 1000 watt per meter square to 650 watt per meter square, the maximum power available with PV shifts only to 77.5 watts. But since we already know that the power required from AC grid and the battery was the same, so during that time, PV will now not be able to supply the overall power demand, and hence the drop in the bus voltage will be seen, which can be seen here. And then the next entity will come and regulate the bus voltage, that is at 48 volts. And the next entity which is regulating the bus voltage here is the AC grid, as it depends on the priority which we are giving to the entities. So the AC grid here comes and regulate the bus voltage as at 48, and here we can see that AC grid is regulating the bus voltage while receiving the power. So similarly, for the next set of values, we can see that when the further irradiation varies and AC grid is not able to supply the overall load demand, during that the battery will now regulate the bus voltage at 46 volts. So these are the experimental results for the same set of results which we have shown in the simulation in this slide. So here we can see that with the irradiation changes here, how the regulation of the bus voltage is being varied by the different entities in the microgrid. So similar to this is the further zoomed in result, that when the PV is regulating the bus voltage at 50 volts, here for this one, we can see that AC grid is receiving the power, as well as for the battery, we can see that this is the battery voltage and around 25 volts at the input side, and the battery is receiving power during this time, 1.4 amperes. So during this time, PV is regulating the bus voltage at 50 volts. Whereas with the change in the irradiation conditions, which we were discussing here, for 46 volts here when the PV is at 300 watt per meter square. During this time, we can see that AC grid is supplying its power, that is 0.72 ampere of current. So during this time, AC grid, PV, both are supplying their maximum power, as well as the now, but the battery is regulating the bus voltage, and the load is taking the required power from the PV as well as the AC grid. And this shows that the PV is working at its maximum power of 35 watts here. So this is the screenshot from the Algar app, which shows that at what instant the PV is working at maximum power point or off MPP. So in regards to the work which I have discussed as per now, there were other related works which were done, that is the layer 2 implementation, which shows the energy resource model and how to determine the power limits of the different microgrid entities was also done. And modeling of layer 2 was done using MATLAB, and the digital simulation study including to showcase the effective real-time power management in DC microgrid of layer 1 with the variation in maximum power limits of temperature, irradiation conditions were also carried out. Also, three-stage charging technique scheme was implemented for the battery system, and for the AC grid, based on the time of the day, the AC grid variation in the power limits of the AC grid was also studied. So for this, I have already published a paper, and if somebody is interested, they can read about the layer 2 modeling as well. The next, the summary of the work which I have shown as of now was that a three-tier modularized model was designed, in which layer 1 modeling was shown in detail. However, layer 2 and layer 3 were also designed, which I have not covered in detail. And the layer 2 includes the energy resources model, and the layer 3 shows the developed model for long durational performance and performance study, and also have discussed the general framework for power management, verifying the assumptions which I have considered in the study, that is the consideration of the higher level model, and also verifying the digital simulation and the experimental results. Now coming to the next objective of the work, which I am showcasing in the present slide, is to carry out the analysis for the selection of the different voltage levels in the microgrid. So in the present work, different voltage levels were considered, that is 50 volts, 48 volts, 46 volts, which I was showing in the previous results. So we came on selection of these voltage levels, considering the following situations. So considering the different perspectives. So those I will be discussing in this present section. So this present objective includes the is the study to carry out the analysis for selection of the voltage levels and to study the effect of cable voltage drops in the microgrid network. So this objective has sub objectives, which includes to investigate the various factors which affect the selection of voltage levels and their different trade-offs for a typical DC microgrid which operates using a distributed type of technique which we are discussing, DC bus signaling technique, and to propose an analytical approach to carry out the analysis for the selection of these DC bus voltage levels, and also to study the effect of the cable voltage drops. And from the particular study which I am discussing in this section, the validation of the limited extendability of this scheme, which I am discussing in the slides, is also determined. So there are various factors which affect the selection of these voltage levels. So the DC bus voltage variation within a predefined range, that is, for example, I am speaking about 43 volts to 50 volts. So the variation in this particular range is the inherent feature of the DC bus signaling scheme. Also, this overall range of the voltage is defined considering the load, the range of load variation, the range of variation of voltage which is allowed by the loads which are taking into consideration. And also, if these voltage levels are very close to each other, for example, if we consider 50 volts, 49.5 volts, 49 volts, in that case, with the small variation in the voltage, false mode transition may occur. So very small voltage levels are not considered because of that. And also, if the voltage levels are not close to each other, that is, overall bus voltage variation range will increase. For example, if I consider the voltage range to be 5 volts for each differences, that is 50 volts, 45 volts, 40 volts. In that case, the overall range of variation will increase, which is not permissible with the loads which are available in the market. So, choice of the voltage level depends on the different factors, which are like microgrid architecture, then the type and length of the cables, and the number of entities in the microgrid, and the acceptable voltage drops depending on the loads which are being considered and available in the market. So in our analysis, as I already showed, that the chosen range of voltage levels was 2 volts, with which the complete analysis is done. To analyze the effect of line voltages drops on the power management, DC microgrid model in the previous section which we were showcasing is now extended to include the resistances in the study, so that we can see that with the addition, with the resistance in place, how the voltage drops is being taken, how the voltage drops is being done, and how it is taken into how the study approaches further with that. So analytical analysis is also carried out for the selection of the voltage levels and is validated through the simulation results also. So for example, here I have considered this microgrid. This is the same microgrid, only we have considered the non-critical and critical load to be one, which is in the form of load, and all the different entities are the same, the AC grid, battery, and the solar PV. So here the cable resistance calculation is done based on the cable length and the temperature, which and also on the ohm per kilometer value of the cable, that is which varies from the type of the cable as well as the current rating of the cable. So here the entity PV is being shown as a voltage source. That means the overall power required by the other entities is comparatively lesser than the maximum power availability of the PV. So this is one of the cases which is shown here. And to carry out the study of the selection of voltage drop, different voltage nodes are defined, that is VA, VB, VC, VD, and VE. So for carrying out the further analysis, the modified nodal analysis is applied, which gives us this particular format of matrix. So here the AE is an enhanced matrix. X is the column vector of unknown variables, that is the node voltages and power exchanged by the voltage sources. And this is the column vector of the known variables, which you already know, that is the power exchanged by the current sources and the voltage source voltages. So for the previous microgrid model which is being considered, this is the modified nodal analysis using the MNA. This is the um this is our matrix which is obtained. So here the worst case with the inclusion in when the matrix needs to be designed, the worst case situation needs to be taken into account. That is, for example, in level 1, if we can consider, the worst case situation will be when the R1 will be having the maximum drop, maximum voltage drop across it. So if we know that the worst case situation is fulfilled, we will be sure that the other conditions which are below that will already be acknowledged. So here the study, the analysis, the framework was that we analyzed the situation for the worst case situations. So here when the R1, the maximum voltage drop is occurring, that analysis is being taken into consideration. And this will occur only when the PV is supplying its maximum current. The maximum current will lead to the maximum voltage drop here. So, further to this, the study was carried out in the simulation as well as in the hardware study. And the system which was considered for carrying out the study in the simulation was for 2.5 kilowatt and 48 volt system. And the copper XLP cable was considered after analyzing the literature by doing the literature survey that what kind of cables are generally preferred. And the overall mm, current limitation for this cable was considered to be 71 amperes for the study, considering the overall power rating of the system. And this was considered for a three single core unarmored and armored cable. And this can be seen in this standard, which is which is shown in this one, reference 12. And the maximum DC resistance of the selected cable was 2.2 ohm per kilometer for a maximum of 90 degrees Celsius. So 90 degrees Celsius, as I already said, that we are testing for the worst case scenarios. And if the worst case scenarios fulfill, then we consider that the previous one would have been which have been fulfilled already. So, however, we will not be reaching these temperature ranges, but we tested it for the considering the worst cases. So, in real time, the DC resistances could be much lesser, but here it is considered to be 2.2 ohm per kilometer. And also the maximum powers for different entities were defined as shown here. That is, initially the PV maximum power was considered to be 1200 watts, which was then varied to 800 watts in the different time ranges to study the different situations and how in the real time if the radiation is varied or if the maximum power availability or the discharging or charging power varies, how the system is affected. The study was carried out taking into consideration the effect of increased cable lengths. That is, the microgrid entities were initially considered to be 10-meter apart, considering the 10 square cable. And then the microgrid entities were 100-meter apart, considering the same 10 square cable. So the overall study was carried out to showcase that as the extendability of the microgrid increases, the scheme which we are looking into, that is the DC bus signaling scheme, has a limitation, and those limitations can be uh, those limitations can be recovered, and like how we need to work on it is also seen in the further slides. So this is just a general outcome which is shown here, that with the 10-meter apart system, the voltage drops in the cable was lesser, as we are studying the voltage drops in the network, and the effective power management study was shown. However, when the entities were 100-meter apart, the false switching of the elements was seen in the microgrid network, and the selected threshold voltages were not affected for this particular case, and the power management in the system was interrupted. So, for effective real-time power management in the DC microgrid, considering the case 2, the cable of higher cross-section area needs to be considered, or the predefined voltage level needs to be far apart, that is greater than 2 volts, which in real time is not a good practice, considering the overall range of the voltage variation available with the DC loads. So it depends that if the DC loads are available in the market, which has a huger range of voltage variation available, which are generally very less and will definitely leads to the addition in the cost. So that is what this point explains, that that this technique has a limitation of extendability. However, it is effective for for small microgrid systems. So this I'll explain with the simulation results. That here we can see that there are these are the different voltages of different entities in the network, which are being shown at their respective nodes. So that is VA, VC, VD, VE, and these are the powers. So this is the simulation case when the entities are 10 meter apart. When the entities are 10 meter apart, during this case, PVs during 0 to zero point 0.1, we can see that PV is regulating the bus voltage here. This shows the logic whether the PV is regulating, AC grid is regulating, or battery is regulating. So here we can see that PV is regulating the bus voltage at 50 volts, and the other node voltages are 49, 49, 49.3, similar to that. So here PV is supplying 1100 watts of power, which is being supplied to AC, battery as well as load. But during 0.15, around 0.15, here we can see that with the drop in the bus voltage here, AC grid is regulating at 48, and the other voltages are 48.3, 47, 47.6 in this phase. And the overall system shows that only one entity regulates the bus voltage at a time. So the optimal voltage regulation can be seen here, and also optimal entities are also being optimally used. The power from the different entities are being optimally used here. So effective real-time power management is being achieved in this particular case. However, when the entities are 100 meter apart, during this case, we can see that or different entities try to regulate the bus voltage at the same time. If you can see from 0 to zero point 0.3, different entities are trying to regulate the bus voltage. And also the entities are not effectively utilized. For example, the PV power available is 1200 watt. However, it is working only at 550 watts. And also AC could have received the power, but it has started supplying the power. So the entities are not being optimally utilized, and also the effective real-time power management is not achieved in this case. So this similar to this, the analysis was done in the hardware case, which wherein the entities were kept 50 meter apart, and the entities were shown to be regulating the bus, whereas when the entities were 500 meter apart, different entities try regulating the bus voltage at the same time. So the overall study, from the previous simulation and the experimental results, it showed that as the extendability of the system is increased, there is the limitation of this scheme, that different entities might have the misconception of the different modes, and hence they together try to regulate the bus voltage, due to which is not in real case can be an effective technique for implementation, because the power will not be managed in real time, and different entities will not be optimally utilizing the entities in the microgrid. In addition to the work which I presented in this objective, various other studies were done. That is how uh, the network or the studies varied with the addition of new entity in the microgrid, with the addition of new voltage level, that is, as we were talking, 50, 48, 46, 44. So how the overall range is varied. Also with the addition of entities with the droop control, that if we are implementing the droop control among the different entities, how the network is affected, and how if the entities are added without droop control. So the study is already published, and if somebody is interested, they can go ahead and read the research in the same background as well. So with this study of the objective 2 which we were discussing, the various factors which affect the selection of these voltage levels, and what are their trade-offs was studied, and an analytical approach to carry out the analysis with the selection of DC bus voltages was proposed, and the results which were obtained with the study were validated through the simulation and the hardware results. And the effect of cable voltage drops in the DC microgrid DC bus signaling scheme was studied, which showcase the limited extendability of the scheme in terms of distances among the entities and also in terms of addition of new entities in the microgrid. The next subsection or the sub-objective of the work was to implement the different energy management scenarios. So the qualitative and the quantitative comparison of the energy management scenarios to show the choice of various energy management scenario has the implication on the sizing of the microgrid entities was studied. So this shows the different energy management scenarios, some of the energy management scenarios which were designed. So in this case, the renewable energy source is always given the priority for the power available with the renewables. However, for the battery and AC grid, the different entities as well as for the loads, the different entities can be prioritized to regulate the bus voltage. For example, in case energy management scenario 1, the battery is prioritized over the AC grid, followed by the non-critical and the critical load. In the similar way, if we can see the energy management scenario 2, so here the AC grid was prioritized compared to the battery, followed by the non-critical and critical load. So here we can see for the layer one, for the MS1, battery needs to fulfill the power demand from the AC grid from the critical as well as non-critical load. So battery needs to be designed at a higher end, that is, it needs to be designed to consider the higher power demands. Whereas if the battery is considered as a backup in the EMS2, during that time, the AC grid needs to be designed to consider the power demand from battery, non-critical and critical load. So this has the specification of designing of the battery converters as or in the other way we can say that for the inverters in the case of the AC grid. Also, if we can compare the and in EMS3, in this, the non-critical load is also shifted way above compared to the AC grid, compared to energy management scenario 1. So this says that if the battery is unable to supply the overall power demand to all these, first of all, the critical load needs to switch off. Then the AC grid needs to provide. So there are different energy management scenarios which can lead to the limitation on the sizing of the different elements in the microgrid. So these energy management scenarios were proposed, and this is the same analysis which is shown that considering energy management scenario 1 and 2, we can see that in energy management scenario 1, the smaller size battery with respect to energy management scenario 2 can be designed because in case 1 only the load receives the power from the battery, whereas herein the AC grid and the load both receives power from the battery. But if we can see the other way around, here the bigger inverter size needs to be designed because it is supplying both battery and load, whereas here the AC grid is supplying only the load power. So it depends on the user perspective that what are the user requirements and how the different energy management scenarios can be taken into consideration. So same study was done through the simulation platform. So here we can see that this is case 1 for energy management scenario where PV, AC grid and battery is shown here. So in this case, we can see that, for example, this is a battery. So in this case, you can see that battery power is not at all being utilized. Battery is only charging here, and in this case, it is charging here. However, it is not, the battery power is not at all being used here, and hence the battery can be designed or resized for a smaller value of the power availability for in this particular case. And as we can see that inverter is being utilized to its peak. If we compare this to the other case wherein the PV, battery and AC grid, the priority has changed between the AC grid and battery. So here we can see that the battery is being utilized, maximum utilization of the battery, but it also comes with all the costing and the life cycle of the battery, the decreased life of the battery, and That all needs to be also taken into consideration based on the user perspective. Whereas we can see that the reduced like the battery here and the reduced inverter pricing can be done because the inverter is not being used here. So the energy management scenarios based on the variation in the voltage level priority, different entities can be prioritized based on the user specification of the perspective. Similarly, the experimental results were carried out for this one to show how the different entities can regulate and how the sizing can be taken into consideration. And also the qualitative comparison of the energy management scenarios was taken out considering a limited time duration and how the entities are prioritized. For example, here the PV AC grid battery and load, and here PV battery AC grid and load. So the overall energy being utilized is this 126000. However, here we can see that AC grid is using 57,000 and a battery is using 6,000. Whereas in the other case, the battery is using 51,000 and the AC grid is using 12,000. So the designing of the different converters and the sizing of the battery can definitely depend on different factors and can be taken into consideration for this analysis. So this particular investigation shows that the choice of various energy management scenarios has implications on the sizing of the microgrid entities. The qualitative and the quantitative comparison of the energy management scenarios was shown and was validated. And to showcase the comprehensive behavior of the developed model and to achieve different user-defined objectives, these energy management scenarios have been implemented in the layer 1, which I showed for the modularized model of the microgrid. So coming to the conclusion of the work, the overall conclusion for all the objectives which were portrayed in the previous slides, modularized model based on a particular logic was developed for a microgrid, which included layer 1, layer 2 and layer 3 modules, in which the layer 1 was a basic power management model, layer 2 was an energy resource model, and layer 3 was a long durational performance and economic analysis model. The focus was majorly on layer 1 model for this work, and the digital simulation and experimental results which showed the effective real-time power management in the microgrid using distributed DC bus signaling was showcased, showcasing multiple energy management scenarios. And the analysis was carried out for the selection of the voltage levels, which was helpful in choosing the type, size, and length of the cables in the network. And it also showed the it also showed the limited extendability of the microgrid, which with the type of control strategy which we are uh, showcasing here. And for limiting the voltage drops which we have shown, the minimizing the cable resistance, either the cable of higher cross sectional area could be selected or the length of the cable should be limited, as we showed that 10-meter apart or 100-meter apart. So if the entities are closer, then the power management scheme was working fine. However, with the increase in the length of the cable or the increase in the distance among the different entities, the power management scheme fails. And also the modeling framework which was implemented showed the implementation of different energy management scenarios by changing the voltage level priorities of the different entities to achieve different economic and performance objectives. So these are some future scopes of the work, and it's great that if a work has a future scope and a perspective to work on further. So the extendability is one thing which I already focused on in the slides, that it has a limited extendability and can be investigated further for increasing the extendability of the scheme, which is one of the limitation of the scheme. And also the long durational performance analysis of the microgrid, that is the layer 3 modeling of the microgrid, was not done in very detail. The work was proposed on a lab-based microgrid, but we believe that our experimentation and proposed modularized model has important real-world implications as well, and the long duration study will allow to carry out the performance and cost analysis of the microgrid over a period of time, that is for a day, month, or a year as well. So that can be one of the future scopes of the work, and also the further detailed analysis of the energy management scenarios, which was the part of the last objective, can also be done. So these are some future scopes, and these are the few key references which could be considered for further study by the joinees. Thank you, and I always say that towards the greener world.
Okay, okay. So lengthy and so technical talk, Akansha Garg. Yeah,
Okay,
yeah, yeah.
okay,
So
sir.
yeah, maybe many power electronics people are there. So now time
Yeah,
for questions. Yeah, time for
yeah,
comments,
sure,
questions.
sir.
Yeah,
Sure, sir.
yeah. I request participant to have some questions with the speaker. Yeah, yeah, yeah. Questions is open now. So please feel free to ask. So in the chat box, one has comment there. Akansha, are you able to see, or I will read it for you?
Yes, yes, sir. I'm able to see. I'm
Okay.
just reading it.
Yeah.
Imagine having two power sources, a battery with voltage of 12 volts and a fuel cell unit with an open source voltage of 24 volts and a peak voltage of 12 volts. These sources are connected to a DC bus from which a motor draws power 12 volts 50 watts following a specific drive pattern. Then the current demand from both fuel cell and the battery aligns according to the load requirement. Now let's consider a possibility. Is there a way to independently control the power output from the battery and fuel cells? This way allow any surplus power generated by the fuel cell to be used for charging the battery, creating a harmonious energy exchange.
Lengthy
Yeah,
question.
so yeah, no, so it's like basically the question is that how the power can be managed, like if there are three sources which are said to be in terms of a battery as well as a fuel cell, and there is a load which is in terms of a motor which is drawing it. So the scheme here which I am discussing is what, like for a central controller, if there is a centralized control and there are different entities present in the network, at that time the central controller reads the bus voltage and tells, okay, this is the bus voltage and how the power needs to be settled. For example, if I consider my case in which a distributed in which there is a distributed controller for all the entities, in this case what happens is like you have already predefined the different priorities for the entities. For example, PV is there, battery is there, AC grid is there, or we say fuel cell is there. So we have already predefined the battery priorities, fuel cell priority, or a motor as a load priority. So to answer this question, for example, battery and fuel cell are two entities which are supplying the power, and motor is a third entity which is receiving the power. So motor is definitely at the lowest priority to supply because it cannot supply, it is only taking the power. So motor will be asking for the power from battery as well as fuel cell. It does not take into consideration that from where it is getting that power. It just know that okay, I need 20 watts of power. It depends on your defining of the priorities in terms of voltage for battery as well as fuel cell. That for example, battery is regulated at 50, So battery will try to supply its maximum available power to the motor first, and then the second priority will be given to the fuel cell, which is a second source in this case, which will then supply the remaining power demand of the motor. So I think I answered the question which is being asked here. If I'm not right, and if you have further questions, then I'm open to like answering it. You can definitely write back to me if that answers it or not. So a controller will give an idea of the amount of power output to be produced by sources, the hardware to set source priority. Uh, so yeah, the local controller will give the idea based on sensing of the demand as well as the available power with the sources. The local energy controller in my scheme will give the idea that how much amount of power is required by the load and how much needs to be sent from the from the battery or from the fuel cell. What is this? To be the hardware to set source priority is called. I think the last part of the question I didn't understood that. Is it a fill in the blank or like what?
Vijay Karthik?
The
Yes.
hardware to set source priority is called. There's no hardware to set the priority. It's like uh, if I say that it's just in the terms of setting the priorities. For example, if I'll share my screen and explain you better. Sir, is my screen visible?
Yeah, it is coming. It is coming.
Okay, okay. So here, if I can say that this is the one who is doing all the play, the local energy management unit. Based on, for example, for this one, I have defined the priority as one, which is a solar panel for me, and this is a priority two, which is a battery. For example, as you said that this is the fuel cell, this is the battery, and this is a motor in the example which you are portraying to. So here, if this is the this is given the priority one based on the bus voltage. So if it detects the bus voltage as at 50, for example, and this is at priority one, that means based on the bus voltage detection, this local energy management unit knows that the fuel cell already has a much more power available with it compared to the power required by the load. Whereas if the voltage drops here, then all the entities will see the voltage drop, and this voltage drop will define that okay, the load required has increased and the power availability has decreased. In that case, the load the priority will shift to the other entity to supply the overall power required by the motor in the case. So now the priority will shift from fuel cell to the battery. So this basically local energy management unit plays the main role to define how the priorities are changing. So this part is not playing the role in the hardware. This is based on the predefined set of rules which are defined for the complete set of network. Uh,
Yeah. So
so is my
Yeah,
yes.
Vijay Karthik has responded. Great, thanks for the presentation, ma'am. I will definitely go through the paper and get back to you in future.
Yeah.
Yeah, Dr.
Thank you
Akansha,
very much.
can you
Yeah.
put your email ID here so that participant can
Sure, sure. You can
contact?
definitely
Yeah,
reach me.
if you are no problem with that.
Yeah, definitely. I'm always happy to
Okay.
answer my research work.
And Nasreen Banu has asked,
This is,
can we?
yeah,
Yeah,
this is my email ID.
okay,
Anybody, if you would like to ask any questions regarding my research, I'm very happy to answer them.
yeah. Another
Yes.
question is, can we apply group control method?
Yes. Definitely, we can apply the droop control method in this one. And I have done the analysis as well as study, including the droop control, including the implementation of the droop control methods in the design microgrid as well. The objective two, which I was discussing, that the study of like the voltage drops on the complete system. With that, I have done the droop control study as well, and I have a paper on it. And please feel free to contact me if you have any further questions regarding that. Also, there is one more question, ma'am. Which control method is best to apply for DC microgrid? So, control as in here, if I talk about the power management strategies, there are different strategies which I have focused on, but I have considered the distributed one, considering the advantage that it was fit for the overall aim which I was considering, that is for the rural electrification or for the remote communities to be electrified. However, the centralized control as well as the decentralized control techniques have their own advantages along with their limitations as well. So I cannot vouch that distributed control technique is the best technique, but depending on the application status, like where you want to apply this technique for, there are always pros and cons for a technique which is being discussed. Yeah.
Yeah. Any other questions? Can unmute and talk to but also is
Yeah, I have one basic question.
Yes, sir.
What could be the maximum power level which we can say that it can be called as a microgrid, and also what is the area? Is there any defined area that this much square kilometer if you are covering, then only it is will be called as a microgrid, or there is no strict definition to this?
Sir, actually, as per the literature, there is no particular limitation on the range of power or if you can say in terms of kilometers. That is still a question, and researchers are like doing research on it and discussing on it, because there are a lot of terms like microgrid and uh, uh, if we say that macrogrid is also there, which is being worked on by people. So, but it said that if it is in a range of few of kilowatts, for example till 10 of kilowatts or 20 kilowatts, something like that, if you are working in the hardware scenario, some thousand hundreds of kilowatts, during that time they are generally considered to be in the range of microgrids. So but there is no specific term which we can say that okay, 1000 watts or 1 kilowatt, nothing like that. That number is still not there. And also based on the extendability, generally people say that it is in terms of a, for example in terms of a city, or in terms of a nearby network, or for a building. It's for a building or for nearby buildings which are connected, it's said to be a microgrid. But if it goes from city to city, then it goes with smart grids and like macro grids and like that. So still the work is being done in that area. That I also went to a conference during my PhD, and this was a discussion, like a huge discussion was that how can we say that it's a microgrid or a microgrid, because the fixed number is not yet there in the papers or in the literature. So I think this is the area which is still being explored a lot, and lot of work is still being done. So that's what I was showing, that the limitation of the microgrid based on the extendability is one thing which is basically being worked on by a lot of researchers. So definitely somebody can do research in the same field and like bring out the numbers on paper that okay, this is what is the microgrid. So not as of now, it's not there. Yeah.
Okay.
Yes.
Thanks so much.
Thanks.
yeah. Any questions further? Anybody would like to ask? If no questions, now I'd like to convey my sincere thanks to Akansha Garg for accepting to be one of the expert talk and given very nice talk and answer all the questions politely and share our
Thank you.
contacts. So, on behalf of organizing team, I'd like to share a virtual token of appreciation to the
Yes.
esteemed speaker. I hope you are able to see it.
Yes, yes.
Yeah. So, thank you, Dr. Akansha Garg.
Thank you very much, sir. Thank you for inviting me for the talk. It's always great to have discussion with different scholars and faculties and to convey our research on the platform. Thank you very much for the time, and I'm very thankful to Shivam sir as well for all the coordinating and for inviting me for the talk. And thank you very much. Thank you.
Thank you.
Yeah.
Thank you
Thank you.
so much.
Thank you.
Thank you so much.
Okay, sir. See you, sir.
Yeah.
Okay, so we will have our next session from 5:50 p.m.
Oh, not 5.
Sorry, 4:50 p.m.
Okay.
Okay. So we'll
Okay.
meet at 4:50 p.m. for the last
Okay.
session of the day.
Yeah. Thank you. We'll meet at
Thank you all. Thank you.